Hi everybody and welcome to the CERIAS Security Seminar here at Purdue University. It is my great pleasure to introduce today Mark Guido from MITRE, and he will talk about how to detect maliciousness using periodic mobile forensics. Mark?
Thank you. All right, so I'm going to give you the results of some research that we did last year. My team and I just completed it this past summer. And the project was detecting maliciousness using periodic mobile forensics. And if anybody has any questions, get my attention, shout them out. Okay, so let me give you an outline of what we're going to talk about. First, we're going to talk about the mission assurance innovation area at the MITRE Corporation. Then we're going to examine the mobile research that's currently going on. We're then going to take the view of an adversary and walk through what's called a mobile kill chain. Then we'll talk about the problem that we were trying to tackle in the research, our solution that we ended up implementing, the experimentation that we did using real malware, and then our future directions. Okay, so the MITRE Corporation has a rich and diverse research program called the MITRE Innovation Program. This mission assurance innovation area is actually one of over 20 innovation areas. And I just listed the research outcomes: to cause cyber adversaries to move slower, to spend more, and to take more risks, and to build a defendable IT infrastructure. Now, this mission assurance innovation area is made up of 5 portfolio areas. And the one that we're going to really look at is the MOXIE portfolio, or the Mobile Computing Security Initiative. So let me show you some of the projects that are going on inside the MOXIE portfolio. Basically, a lot of our projects are geared towards the Android platform, but we do have a little bit of iOS work that we're doing. We also have 3 projects that are in the proposal phase, so they aren't listed here. And we also have a full lab that we're doing smaller projects in. Now, I highlighted 2 projects here. The first one is the project that I'm going to primarily focus on, detecting maliciousness using periodic mobile forensics. And I highlighted the mobile system integrity measurement project. Now, these projects are very related. They actually make up the measurement portion of this portfolio. And they're related also in the fact that detecting maliciousness using periodic mobile forensics would be focused on user behavioral measurement and potentially malicious application measurement and the system security integrity measurement project is really looking at the various structures of the operating system and taking measurements of, for instance, the kernel. And then once you can trust the kernel, you can trust other higher level operating system structures. So if there's one thing that I want you to walk away with, it's this starting point. Mobile devices are not small laptops, so why are we trying to use various security mechanisms that we've been using with laptops and desktops on inside this new paradigm? These devices are now sensor-rich devices. They're kind of always on, and they're companions. We now walk around with these things every day. Our sponsors, our government customers are trying to push things like BYOD, bring your own device. Anybody familiar with that? I mean, basically what it is you can show up with your personal device and get onto the enterprise resources with it. Now this is a concept that could save money. But I really don't like this concept. A lot of our sponsors need that higher assurance and really should be supplying the phones that their enterprise users are using. There's persistent connections now on these phones or mobile devices, and these connections are now not to the enterprise like we used to have it, but now they're to the carrier networks. So let's look at where we were 5 years ago and where we are now. So 5 years ago, we were in a BlackBerry world. And the voice traffic 5 years ago was sent through the carrier network, but the data, the data traffic, like your SMS messages, things like that, that was all funneled through what's called the BlackBerry Enterprise Server. And because of this BlackBerry Enterprise Server ended up providing a management and a monitoring port for these BlackBerries that you would have in your enterprise. You could actually control what applications, for instance, were installed on the BlackBerry device, and you could really lock it down. Now let's fast forward 5 years from now to the present. The voice traffic is on the carrier network. The data traffic is also on the carrier network. And our sponsors are really struggling to figure out how we lock down these devices so that their employees can take advantage of all these new resources and capabilities that these phones or tablets have nowadays. Okay, so let's take the point of view of an adversary. And what we're going to do is we're going to walk through what's called a mobile kill chain. So this is the Lockheed Martin kill chain. It's a series of steps that the adversary would ultimately walk through to basically attack a device, a resource, or a network. It's been modified. This one's been modified by MITRE a little bit, and it's been modified to really push it in the mobile space. What we have, basically the main concept of this is that if you have a malicious user or maybe a malicious application, this malicious user or application would walk through this kill chain, ultimately not to establish a foothold on the target phone or the target tablet, for instance, but rather to establish a foothold inside the enterprise and to utilize maybe the resources that phone that the phone user might have getting on the enterprise, and then establish an attack vector that way. So let's walk through these phases very quickly. The recon phase would be where the attacker is gathering information about you. And I just have a couple of examples here. You see Pandora's, the application itself that you would put onto an Android phone is collecting information on you. And most times, hey, maybe this is harmless, but there's a lot of information that can actually be tracked. Things like your phone number, phone ID, your location. All of this would be sent off the phone, and it could be used to establish different attack vectors that the malicious application or malicious user could use to attack you with. So then you have the weaponize and the deliver phases, and I've just highlighted an example here that is typical of what we're seeing inside of Android malware. This is a fake Instagram app that could cost unsuspecting Android users. So basically, for a lot of malware, what the malware developers would do is they would take a legitimate application, they would basically download that application, pull it apart, inject their malicious code into that, and make some sort of an entry point in the actual legitimate code, and then they'd be able to put it back up onto some sort of Android market, and an unsuspecting user would come along, download it, and ultimately accept the permissions that new application has, and boom, that malware is now going to be most likely successful on that phone. This is a common vector, and maybe in the way that this is going through the delivery phase, maybe we can do a few things to find that on the devices. Okay, so then we have the exploit phase, and highlighted a couple more here. This top one, root your gingerbread device with gingerbreak. So gingerbreak is a very common exploit that affects the gingerbread version of Android, and it actually goes out and exploits the Valdi service, and we'll talk about this. So the way that the malicious application may be utilizing gingerbreak to do this, maybe we could find these types of things on the static portions of the phone, the static storage spaces, and we can actually locate this and maybe take some action on top of here. And finally, we have the control, the execute, and the maintain phases. And I highlighted another one on here, another example. So the control would be where it's the phase where that piece of malicious code may be going out and contacting a command and control server. The execute would be where, with whatever the payload is of that malicious code, how that payload is ultimately going to be sent to the phone. And then the maintain phase is when the malware is ultimately establishing itself on the phone to survive a reboot. So it's establishing its persistence in some way. And this is foreshadowing again here. Maybe we can do a few things to find how these applications are establishing their persistence. How we doing? Any questions? Okay. So let's talk about the problem that the research was going to tackle. So we've already talked about the fact that in enterprise deployments, we no longer have that BES server that's providing us with a management and a monitoring, an audit point. Actually, a lot of organizations' data is being sent over the carrier networks. And a lot of what's happening is the carriers are going back to these organizations, and they're telling them that they really don't want them to be providing more secure mechanisms. They want them to use the particular operating system versions that you can go out and buy in any Android store, to get onto their networks. So maybe what we can do is we could set up a server that would in fact it would operate like a BES server in our enterprise, and we could have a client that would be on these phones or tablets. That this client periodically is going to send our measurement off to that server for collection, and then we can do offline analysis. Maybe we can take some different forensics techniques and look for these. It takes static measurements of the storage medium, and then do the analysis offline and take some action on top of this. So there was 3 use cases that we tried to tackle originally when we proposed the research, and we only had time for one of them last year. So we really focused on the malicious APK, or the malicious application. When I say APK, it's an APK file that's installed onto a Android phone. So you'll see APK referenced a lot in here. And really what we want to do is we want to take advantage of that sensor-rich information that is on these phones now, as compared to your laptops or your desktops before. These things are being carried around, and there's a lot more information on these and that we can take advantage of. So here's what we did. We ended up going out and we ended up building a client that runs on the phone. We ended up putting a server inside of our enterprise that would communicate with the client. We had an enterprise database that would store all of our measurements, and then we built this analysis framework. This analysis framework really was just a mechanism for us to run various forensics tools on top of our reconstructed images. And I'll show you how we do it. Now, we named this tractor beam because you really can't do anything with detecting maliciousness using periodic mobile forensics in terms of a name. So, we named it tractor beam, and that's a lot easier to say. The other thing that's important to note is that tractor beam was built to test out our theories, and so we aren't looking at putting this on an actual enterprise network, but rather it provides us a platform for doing these measurements, and maybe we'd modify it in the future. But right now it's providing us a great platform for doing this. So let's talk about our approach. And this is the approach from the enterprise perspective. So what we do from the enterprise perspective is we would have a full image of the block devices of the phone that we would have taken beforehand. Now that could be, if it's an enterprise deployment, it could be the first time that you hand out these phones to your enterprise users. Or if it's an enterprise deployment, maybe there's some gold image that you could base all your measurements off of. But we have this at time t, and then at various times after this, what we're going to do is we're going to send data off the phone that would allow us to reconstruct our forensic images offline. Now, we can't actually go and send an entire forensic image of the phone offline. So we had to instead go through a process to scan the hard drive, looking for changes to the block devices, and then only send those changes offline. And then we go through a process that we're going to reassemble the changes. We can't go through this process to send off the entire thing, especially because we're trying to do this over the air. So in an enterprise deployment, maybe as you walk into a building and the phone is in your pocket or a purse, the phone immediately detects that you're on the Wi-Fi network and then would send the measurements off the phone, and unbeknownst to the user, basically. Okay, so let's talk about the process of how we do this. And what we're doing is we're actually doing what we call live phone forensics. So live phone forensics means that we're utilizing the kernel of the phone to provide us measurements. Now, you might say that, hey, maybe there's a piece of malicious code that would exploit the kernel, and so the kernel may lie to us and provide us false measurements. Well, you remember back that system and security integrity measurement project? One of the things that would provide us that trust in the kernel would be if that system security integrity measurement project was running on the phone also, and it was then providing us that trust in the kernel that we can then trust our measurements with. So what we have is the tractor beam service that runs on the phone, and it's started up by the init process on the phone. So init then provides the tractor beam service with the proper permissions that it needs to take these measurements. Now there's a background scan that ends up occurring over top of these block devices, and it just happens in the background. It doesn't take very long to do, and the changed blocks are marked inside of a database. Later at a certain time, those blocks are sent off of the phone, and they're stored in our database. Once they're in the database, we can reassemble those blocks back to the original block devices at that particular snapshot time. And then once we have those reassembled images, those forensic images, we can run forensics tools on top of them, and we can then take the results and we can eventize them. We can put them back into our database, or we could send them to any other auditing system like ArcSight or Splunk or anything like that there might be. Now all these forensic techniques and tools are performed on these snapshots, and they're performed offline of the phone. The only thing that we're trying to do on the phone is that scanning piece, and ultimately then sending the data off the phone. And we do this because we don't want to negatively affect the phone in terms of battery life or the amount of bandwidth or anything like that we're utilizing. Okay, so this is an example of how we go through and reconstruct our images. So inside our database, we would have at time t, we would have some sort of a starting point. And I just highlighted the boot image, the recovery image, the system image, and maybe the data directory here as important block devices that would be on here. Now you have a series of offsets that make up these particular images. And at time t1, you see that 4 blocks ended up rolling in, being sent from the phone. Now they're then put into the database, and if we wanted to reconstruct the images at time t1, then what you would do is you would take those 4 blocks, and they would replace the blocks that were in time t. And so at time t1, in the middle there, you see that we've reconstructed that image at that snapshot time. Now at time t2, there's 3 more blocks that ended up rolling in that had changed. And some of these blocks are in the same locations as your T1 blocks. So what those blocks do is they replace the T1 blocks to reassemble at T2. And so you see there's kind of a mix at time T2 of T1 blocks and time T2 blocks. And that's how we would reconstruct it at time T2. Okay, so these next three slides go over our detectors that we implemented. And this is the first one. What we wanted to do is we wanted to look at the kill chain and we wanted to identify where the malicious code would be going through that exploit phase. So one of the things we did was we looked for where the changes occurred on these block devices when we ultimately reconstructed. We had a lot of good data for where the locations of these changes occurred. And this is a simple heat map that we ended up constructing. You see the bootloader, the recovery image, the boot image, the system image, all those blues up there. From an enterprise perspective, we should rarely see any changes on these. Typically when this happens and the enterprise doesn't know about it, it's bad. Okay, so we can ultimately target these as and if we see changes here, then we want to send up an alert. Now Tractor Beam itself, because of the way Tractor Beam works, it's already set up to find these changes, and so these particular detectors were pretty easy to implement. Now, Android phones, nowadays, the modern Android phones are running the fourth extended file system. So because of that, we can take various forensics tools and we can apply these tools to our reconstructed images and get out some very good results. We ended up using the sleuth kit with experimental ext4 support. This paper that I have down at the bottom here, Kevin Fairbanks, actually, this paper was published in this past DFRWS conference proceedings. Kevin Fairbanks ended up doing an analysis of ext4 for digital forensics, and one of the things that he did was he was instrumental in putting ext4 support into the sleuth kit. And so with that ext4 support, we can use the sleuth kit against many of our block devices that are on the phones, and we can do various things. We can identify when APKs are installed, for instance, and we can actually pull out those APKs out of the reconstructed images and then do some more processing on top of them. We can identify deleted files that might be on the file or might no longer be on the file system. We could reconstruct APKs. We ended up utilizing FIWALK, which also works very closely with the sleuth kit. And we identified all the MACE times, the modified, the access, the created, and the entry modified times from these file systems. And we were able to see any changes that happened from the last snapshot image. And then finally also, FIWALK allowed us to generate what's called DF-XML, which is an XML specification that we can then take and we can send it to other analysis tools, and the other analysis tools would be able to analyze that DF-XML. And we were targeting the delivery phase of the kill chain on these detectors and loggers. Finally, there's a whole event notification system inside of Android, and how this works. APKs can go and register for what's known as the boot completed event, and they have to do this inside of the Android manifest file. It cannot be actually inside the code. You can register for other events inside of the Java code, but this particular event has to be registered for inside of the Android manifest.xml file. Once you've registered for that, the system itself, when it's completed booting, will send an event notification saying just that boot is completed, and the APKs that have registered for this could take some action on top of it. Now the Android Malware Genome Project ended up, this paper down here, the two researchers from NCSU ended up identifying that 83% of their malware that was in this Android malware genome project sample set ended up registering for this boot completed event. And so we made a detector that would go in to our file systems and would pull out any new APKs and look for the existence of this boot completed event registration that has to be there. Now, the typical place where we were going to look for these APK installs was in the data app directory. That's typically where, if you were going to go and you were going to either pull an APK from the market, or if you were going to sideload an application, it would go through and it would install in the data app directory, and then it's usable. And this APK is structured just like it would be as a file anyplace else. We can actually lift that APK out, and it's the actual APK that is there. And we're targeting the maintain phase of the kill chain for this. So here's our 7 detectors and loggers that we ended up putting together that were particularly used for this research. We have detectors 1, 2, 3, and 4, and these detectors alert on changes. Typically, when you see me use the word detector, what I'm saying is that these things alert on things that are bad. So we're alerting on the boot image change. We're alerting on the recovery image change. We're alerting on the bootloader or the system image changes. Then we built a couple of loggers that utilize things like FiWalk or the sleuthkit, and so we were able to go through these loggers, and these loggers would be they'd be mechanisms that would go through and, for instance, identify all the mace times. Now, some of these mace time changes might not have anything to do with the malware that was on there, so that's why they're loggers. We would log that information, and potentially we can build detectors on top of them to mine out the logger data even. So we have one that would go through and identify all the mace times, and then we also identified any deleted files that we saw from the file system since the last snapshot. And finally, we built a detector that went in and identified any APKs that were installed since the last snapshot. It pulled apart the Android manifest file and looked for the evidence of the boot completed registration. Okay, so we had to figure out a way to test this, and what we wanted to do, we wanted to use real mobile malware, but we didn't really have a sample set to use. We ended up reaching out to the Android Malware Genome Project, and we obtained all 1,400 samples that they have in there. Actually, Purdue is also a member of the Android Malware Genome Project, so somebody here has the 1,400 samples. We ended up the problem with this set is that we had no source code for any of these samples. It was just the APK files, and so we didn't know what these APKs were going to do. We didn't know what they would do to our phone, and so what we did was we took this malware into MITRE's Network Attack and Investigations Laboratory, or the NAIL. Now in the NAIL we were restricted in what we set up. We actually used a real phone in the NAIL, and what we did was we didn't give it any wireless. There was actually no SIM card. There was no Wi-Fi. We actually had the phone inside of a Faraday bag, and then we ended up modifying the tractor beam system to send the information, to send the change blocks over the Android debug bridge so that we can collect them off of the phone. So we had to figure out which samples of malware that we wanted to use, and what we did was we took those 1,400 samples and also a few more that we had added that we had, and we looked for the presence of a mount command, and particularly we looked for that word remount. What we thought was that this would be a way that the malware was looking to establish persistence, and largely I think that we were mostly wrong on that. It turns out that a lot of the malware that we ended up using was using that boot completed event registration. This would be a way where the malware was trying to establish not persistence, but its privileges. Maybe, for instance, it would add a binary to the privileged space that was set UID to root, so that they could restart and have those escalated privileges the next time. And from there, we narrowed the sample set down to about 160 samples from the 1,400, and then from there we basically chose the samples. I'll say semi-randomly, even though it says randomly up there. We did have a few samples that we started with that were from the same family, but for the most part, we chose all the samples randomly from there. Now, this is a picture where we plotted all of our 160 samples, and we plotted the relationship to that the malware families from the Android Malware Genome Project had in terms of its relationship to the boot completed event registration and to the default main action. And so you see that there's only some of the samples that had that boot completed registration in there. A lot of them were ultimately using this action main, some of the families. Okay, so for round one, what we did was we took 20 samples, and we went through a process where we installed those samples. We then ended up simulating a user clicking the samples. We actually had this all automated. We used the activity manager to run the application. We ended up waiting a certain period of time, and then we actually threw in a reboot in there before we took our measurements. And then what we did was we restored the image back to a safe, restored the phone back to a safe backup image. And so that was the process we went through for these 20 samples, and our results were pretty good. We ended up seeing every sample install, and they were all installed, well, most of them were installed in the data app directory. I'll get to that. We ended up seeing a bunch of them drop files to the file system, and when I say drop files to the file system, these were actually files that we could identify as being malicious. So maybe these files were called zhash or RATC for Rage Against the Cage. And so a lot of them did that. A lot of them ended up, but not all of them, ended up registering for that boot completed event. And finally, we ended up seeing that one of them ended up going and changing the system image to drop their malicious payload onto it, and we'll talk about that one. So let's talk about these samples, and the first one we're going to look at is actually the one that we failed on, sample 5. So sample 5, we ended up doing some analysis on this, and the reason why we failed was because we couldn't really tell from the information that we collected if the malware was successful or not. Now it turns out when we went in and analyzed this, this malware utilized the Rage Against the Cage binary. This was an exploit that affected Android 2.2 and below. So our phone that was running Gingerbread was not vulnerable to it. In actuality, the ADB service is what gets exploited by this Rage Against the Cage. And sure enough, the ADB service wasn't vulnerable to attack on our Gingerbread phone. But what this Rage Against the Cage does is it spawns processes up to the point where this value r limit nproc is reached. And once it's reached, it will kill the ADB service, and then the ADB service, if it can't set UID to a lower privilege level, then the ADB service stays running as root, and you get a root shell. So sure enough, on our phone, the ADB service was able to set UID to a lower privilege level, and so Rage Against the Cage wasn't successful. But it had a little bit of a side effect here, in that that our limit mproc value was still pushed up to the limit. And so it turns out that our tractor beam service had some code that was trying to execute and actually perform a wake lock by forking off a process, and we weren't able to do that. So bad side effect that we learned from our tractor beam service ended up not working correctly on this one. Now, we didn't see this during the testing because of the fact that we ended up putting that reboot in there. So that reset the R limit mproc value down to where it was normally. And so what we had to do was, in order to see this, was actually run our tractor beam detection without doing that reboot. And at that point, tractor beam didn't work, so we had to go in and modify that. Okay, so let's look at sample 13, and sample 13 was the only one that we saw change the system image. Now, sample 13 was the ginger break APK, which goes through and roots the phone. It uses a version of the ginger break binary, and this APK, most people would probably say that this isn't really malware because the user, the actual phone user, is prompted. Does he or she want to do this? Does he want to root the phone? Now, we didn't really think that this was malware, except for when we look at this from the enterprise context. On the enterprise, you wouldn't want your users to be making the decisions on who can have root on your enterprise. And so this was the context that we were in. And so we ended up saying that this would be considered malware. Now, how this flow goes, the user is presented with a user prompt, and the user has to say okay, and then the exploit is run. Our phone was vulnerable to it. We were actually using 2.3.1, which was the most vulnerable version of the Gingerbread operating system, and so Gingerbreak worked like a charm. And then what this APK did was it remounted the system image and it remounted it read-write, and then it actually wrote another APK that it had in its assets directory, the super user APK. It wrote that to the system app directory, which is different than the data app directory. So what we had to do is we had to look in two places for APKs, the system app directory and the data app directory. We actually ended up rewriting our detection mechanisms, and we went back and ran all the tests again to make sure no other pieces of malware were utilizing this system app directory, and we didn't see any others that were doing it. So round two, we ultimately wanted to focus on the boot completed detector. Now this boot completed detector is the one that takes apart the APKs and looks for that boot completed event registration. And that paper that I had showed you from the Android Malware Genome Project, the researchers from NCSU, they had that figure that 83% of their malware in their sample set used this boot completed event registration, but there was no figure on how often this occurs legitimately. So what we wanted to do was we wanted to go in and we wanted to take 10 malicious applications from our sample set, and then we also went out to Google Play and we downloaded the most legitimate apps that we could find, and we ended up pulling down 90 or so of them that we used in here. Now, the way that we identified that they were the most legitimate apps, we ended up going out and looking for the most popular apps. And what we figured was that the popularity of these apps, with however many people are using them, that would probably mean that there wouldn't be some malicious content in there. And we ended up throwing them in all together, running our experimentation again in just about the same way. And this is a confusion matrix of our results. So our recall was excellent. We identified that every single piece of malware had this boot completed event in it, and we were good there. But our precision was way too low, and it's because of the false positive problem that we had here. So we'll talk about this, but maybe this isn't a very good feature maybe this is a feature that we could use combined with other features inside of some sort of classifier, but it's not good by itself. Now, also 3 APK files were not observed installing in this round, and they were legitimate applications, and they were installed to mount secure ASAC. So this is another place that we potentially have to look to make sure that we cover all the APKs, and we'll talk about that. Our third round, what we did was there was actually, we call it demo malware. This was malware that wasn't really doing anything truly malicious, and we were able to obtain the source code for this. There was actually some demonstrations that this was being used for. And what this malware did, this was actually wrapped inside of a frozen bubble game, if you've ever played that. And this particular frozen bubble game contained malware-like capabilities that were documented in this paper down below. These two researchers from George Mason University ended up theorizing that they can make a phone act like a keyboard to a USB host. The USB host being a laptop or a desktop, and so the USB host would think that the phone, when the phone is plugged in via USB, it would register that as a keyboard, and then the phone itself can deliver keystrokes to the laptop and ultimately potentially control it. So that's what this malware did, and let me show you how this works. This malware wrapped inside a frozen bubble, you actually had to play the game before any malicious code was sent. You either had to lock the screen or you had to lose the game, and then the malicious code was sent to the device and executed. This actually used a weaponized version of Gingerbreak. And it ended up working the same way as that other Gingerbreak that we analyzed, except for there was no prompting to the user. But it went through, it executed the Gingerbreak binary, it exploited the val-d service, and then it remounted the system image, and then it took that super user APK and it threw that into the system app directory. And that super user APK also ends up depositing the SU binary onto the system image. So we were able to see all of that. What we weren't able, then this malware goes and what it does is it uses the DD binary that is found on the Android phones, and it writes over the boot image. Now the boot image, you may know this, is made up of the kernel, and it's also got the initial root file system on there, the mount points. And so when it's rewriting over that, what it does is it restarts the phone, and that new kernel that was in that boot image, that malicious boot image that it had put on the phone, is then run, and that new kernel code ends up going and changing the look of the phone to be a keyboard when it's plugged into a host device. Now, this is our results, and what you can see is that we saw that system image change, we saw that boot image change, and so we were pretty successful there. But what we didn't see was we didn't see the boot completed event registration. We didn't see any files dropped to the file system besides that SU binary, but we didn't see any of the malicious files being dropped to the file system and utilized. And we didn't see this install, and again, it's because it was written to that mount secure ASAC location, storage location. Okay, so let's talk a little bit about our results, and I think we can safely say that we ended up identifying alternative methods for after the fact reporting that an enterprise can use to do that. We can at least say that we can complement certain methods that are being used today, like virus scanning on the phone. These are typical MDMs, things like that. And ultimately, the enterprise can take action and respond. So maybe once Tractor Beam would identify that something has occurred here, you can revoke access to that particular phone to some enterprise resources or something like that. We also showed that boot completed detector is not effective alone, but maybe it could be used with other event registrations. And really it's because of that false positive problem that it had. Maybe it could be used as a feature with other features inside of some sort of classifier. Finally, we wanted to see all the APK installations, so maybe we go back and do something that would generally look at all the files that were installed and identify, in some way identify APKs, because what we found is that we saw APKs installed in the data app directory and the system app directory, which is that privileged location, and then we also saw that mount secure ASAC location. We actually saw another one, the data local temp directory, that when applications are either downloaded from the marketplace or they're sideloaded, the application gets written there for a short period of time and then deleted. The problem with looking there in that data local temp location is that when we installed 10 apps in a row, we only saw the last one. It's because when the files are deleted from that location, those same blocks are being allocated and deallocated, and they're being reused again. And so we only see the last installation that we did before taking a tractor beam measurement. Now this is an excerpt from Andrew Hoag's Android forensics book, and it talks about mount secure ASAC, and really what mount secure ASAC is it's on the SD card, and what it is it's an encrypted location. So the APKs are actually encrypted in that space, and then when they're utilized, they're decrypted and they're put into mount ASAC. So we did see that this was another location that potentially we can lift these APKs out. The interesting thing about this mount secure ASAC, though, from the standpoint of the boot completed event, is that it really cannot contain any boot completed event registration, any of the APKs that would be inside of mount secure ASAC, and that's because, considering that this is on the SD card, this event notification for when the Android system finishes boot up and sends it out, that happens before the SD card is actually mounted. So I guess APKs could have this in their Android manifest file, but they wouldn't get the notification at that point. It happens before it, so there's no reason for them to be registering in this location. Okay, so in summary, the project focused on mobile malware in the enterprise, and we concluded that there are alternative methods that show promise for identifying and classifying on a running phone. I mean, we were doing this live on running phones. We also did a few novel things, I think. What we did was our method for extracting only the changed blocks and reconstructing them. We ended up having a database that we had completely normalized for this, and so we were able to really assemble this really fast based off of what was stored in our database. And then we ended up developing a number of forensics tools and an analysis framework to run them, a number of detectors and loggers. And it says 8 detectors were developed here, 7 were used for this research. There was actually another one that we developed. But really what Tractor Beam did is it provides us with a platform for this past work and also our future work. So what are our future directions? Well, we're funded again this year, and we're going to go back this year and we're going to look at the malicious users. This is really the insider threat problem. So on our enterprise, if we have a user that's doing something, whether it's an inadvertent insider threat or if it's actually a malicious insider threat, we'd want to identify when these occur in our enterprise and then be able to take actions on this. We also want to go through and identify masquerading users. Now, masquerading users are users that may be impersonating the actual phone user. And sometimes this might not be bad at all. This could be, maybe the phone user ended up, lending it to their kids to make some phone calls or play some games, or it could be, that the phone user left the phone in their hotel room, and all of a sudden the phone is trying to go and call out to use enterprise resources. So in both of these situations, we want to identify when this type of thing occurs. And we want to do this based off of behavioral usage information that we can collect. Finally, we want to take our system and we want to pull it out of the enterprise context, and we actually want to apply it to the forensics lab use case, where we might not have prior knowledge of our phone, and we definitely don't have that gold image that we originally started with. How do we go and take these same methods that we were using and apply them in that use case? So that's some of the things we're going to be writing about this year. Now I have on here the CERIAS collaboration, so let's talk about that. We want to actually, I'm in talks to have this mass grading experimentation happen later on this year. What we would do is we'd take volunteers, student volunteers, and we'd supply the student volunteers with a phone that would be running the tractor beam system. And what we do is we would just for a period of time we would train our system. We would take the measurements and these users, we'd want to just use them normally. After a certain period of time, what we want to do is we want an arbitrator to step in and swap the phones between the users. And then we'll take some more measurements, and then we'll go through that process to swap the phone again, and maybe we'll do this a few more times. And really what we want to do once we collect all this information is we want to be able to identify the users paired up with the phones at various states in our test. And we want to do it solely based off of the behavioral usage information that we collected. So hopefully this is coming to a campus near you, probably later on this year, into next semester at some point. And that is it. Do we have any questions for me? Thank you.